Our last lecture of the day or last lecture of the week, right? Final speaker is Rohit Jain from the University of Texas at Austin. He'll be speaking on the fully nonlinear stochastic impulse control problem.
Okay, thank you very much. I want to start by thanking the organizers and the scientific community for giving me an opportunity to speak here today, and having a lot of fun in Rio and enjoying all of the talks. So thank you very much for this opportunity. I want to talk to you about a problem that I'm currently working on with my advisors, Professor Caffarelli and Professor Fegali. I'll present to you some work that we've completed, and then towards the end, I'll mention some work that we're considering, kind of as work in progress at the moment. So the title of the talk is Fully Nonlinear Stochastic Impulse Control Problems. So I'll probably start by first giving a brief outline of what I want to do. So I'm going to start with an introduction where I'll introduce the mathematical model of a stochastic impulse control problem, and then I'll formulate the problem that we're interested in solving. And then I'll move on to studying some estimates for such generalized obstacle problem. So I'll formulate what I mean by generalized obstacle problem. And the estimates that we obtain in step 2, I want to apply for the stochastic impulse control problem in step 3. And so that will complete the circle and allow me to give you some estimates that we've obtained for the impulse control problem. And I'll end with a conclusion about future work. Okay, so the mathematical model. So stochastic control theory, just impulse control theory that I like to think about. So there's classical control theory where you have continuous monitoring and you can intervene continuously on your process. And you have these types of problems which are like optimal stopping time problems where the controller kind of only has to decide to intervene yes or no. So somehow in between you have these impulse control problems where you can kind of intervene when you'd like, but there's a transaction cost for each intervention. So another name or another way I like to think about this problem, if there was ever a theory for parenting, I feel like this would be an integral part of that, because in some sense if you let your process move like a Brownian motion, let's say, and there are some regions in which you intervene and there are some regions in which you don't intervene. So somehow whenever the process gets to beyond some area, you intervene and you bring the process back. You incur a cost when you do this, but you're able to arbitrarily bring the path back into the non-intervention region. And when you do this, so in some sense, for these types of problems, what you end up studying is the so-called intervention operator, which characterizes what is the optimal strategy if you were to intervene at the present time. This is what you would have to evaluate, where U is kind of like the expectation of the value function for this stochastic process. So represents the value of the strategy, and so like as I mentioned, the controller can instantaneously move the state process by a certain amount every time that they'd like. So when you do this, when you study this type of problem, you end up with the following inequality: U of x is less than or equal to mu of x, because it's not always optimal to intervene. So if you do intervene, the cost, the value function is mu of x, but sometimes it's not optimal to intervene, so the expectation value should be less than or equal to mu of x for every x. So from the analytic perspective, one can obtain an obstacle problem. And in the obstacle problem here, for the classical stochastic impulse control problem, with diffusion, you have the Laplacian, and your U of x is less than or equal to mu of x everywhere. So the key feature about this problem is that mu of x actually depends on the solution U. So this kind of makes it not the classical obstacle problem, because a priori you don't really have much regularity on the obstacle. So the problem that we're going to be interested in here is actually kind of like the first half of the regularity theory for free boundary problems of obstacle type, and just trying to prove estimates on solutions to these types of problems. So, okay, so here are some remarks on some previous work. Existence and uniqueness of a continuous solution. One can prove this by an iteration technique where you study classical obstacle problems, and in the limit you can obtain a continuous solution for the stochastic impulse control problem. Here are some authors that have worked on this and have shown different types of ways of converging. And then let me mention, so there's work by Caffarelli and Friedman and Benoit Pertencem, where they proved the optimal C11 estimate for solutions for divergence and divergence operators admitting some sort of smooth coefficients. So, right, so in some sense, we will come back to the Caffarelli-Friedman approach. That's going to be important for us when we study the more general fully nonlinear problem. And let me just make a quick comment that stochastic impulse control problems are a specific class of problems in this more general theory of quasi-variational inequalities. So Professor Caffarelli mentioned to you how you do a minimization technique over a convex set. In some sense, this convex set for quasi-variational inequalities depends on the solution U. So these are more general classes of types of obstacle type problems you can consider. Okay, so let me state the problem that we're interested in. So we're going to study a fully nonlinear uniformly elliptic operator, and we're going to assume some sort of convex and convexity or concavity assumption in the Hessian variable. This is so that we have some sort of interior a priori estimates away from the contact set. And we're going to define a more general stochastic impulse control operator here, where we have the same inf term here that you saw before. But here we're going to allow, instead of 1, we're going to allow for a more general semi-concave function. Here we're going to assume strict positivity, bounded, and it's decreasing in the positive cone. So this operator, so for the two-dimensional picture, if I want to evaluate the operator here, what it's saying is I have to scan out the entire positive quadrant and look for the infimum value out there. And so this assumption on phi is that phi is just positive in this cone here, where I have to scan for the operator. Okay, so let's consider, so this is the problem we're going to consider. We're going to consider a fully nonlinear version of this problem, assuming 0 boundary data. Let's assume right-hand side 0. And the main theorem that we're able to show is that the solution to this fully nonlinear stochastic impulse control problem has a modulus of continuity omega r up to C11. So in some sense, so what we're showing here is, so here we're assuming a modulus of semi-concavity on this function phi of x, and somehow we want to propagate that semi-concavity estimate from the obstacle to the solution u. So the other thing to note for this problem is that in the classical obstacle problem, you kind of had a modulus of continuity on the solution, but here we only kind of have a one-sided estimate. So in some sense, we have a one-sided estimate, and we're going to propagate a one-sided estimate into a two-sided estimate on the solution. So that's something that we'll come to later. So what's the idea? So okay, so to study the fully nonlinear problem, we're gonna keep that to the side for a moment, and what we're gonna do is we're gonna look at a generalized obstacle problem. And so the technique in Caffarelli-Friedman was to show that mu, when instead of phi we had just 1, is that mu admitted kind of an almost concave behavior or a semi-concave behavior for mu. So, and what I mean by that is essentially you should think that in a ball of radius r, you have a uniform parabolic bounds from above for the obstacle. And so that's maybe a linear modulus of semi-concavity, let's say. And so what we're going to do is we want to study this following problem here. And we're going to obtain estimates for solutions to this problem. So we're going to start by saying that phi u, we're going to assume that to be a semi-concave function with a general modulus of semi-concavity omega r. And then we consider this boundary value problem for the fully nonlinear operator. And so what we want to show here is, in fact, for this problem, that the obstacle phi u, when it admits a modulus of semi-concavity omega r, then the solution has a modulus of continuity omega r up to C11. And when we have that, then one can go back and apply to the stochastic impulse control problem. And the point of applying it to the stochastic impulse control problem is that we, in fact, want to show that this omega r semi-concavity for phi of x is the same semi-concavity modulus for the operator itself. And that's the idea. So once we prove that the obstacle inherits this semi-concave behavior, then we can apply this theorem, and that's going to allow us to conclude this theorem here, the first theorem. Okay, so that's kind of the plan. So those were the two main theorems that I wanted to present. So let's see. So just as a remark, as a corollary to this theorem, you can recover the sharp C11 estimate proved previously by Caffarelli and Friedman in the diffusion case. So like I mentioned, the goal is to kind of obtain a uniform modulus of continuity omega r for phi u. We don't attain a full modulus of continuity for phi u, but you can obtain it, let's say, on the contact set, and that's kind of the idea. And as I mentioned, the first theorem follows from the second theorem once we prove that mu of x admits a modulus semi-concavity omega r. Okay, so that was a strategy. So we're going to study this generalized optical problem and prove an omega r of modulus of continuity for the solution. So we're inspired by the initial, and I believe this is where I first read about it due to Caffarelli-Kindler-Lehrer, where if you look in the neighborhood of a contact point, the modulus of continuity of the obstacle propagates, so the solution lifts away from the obstacle with the same modulus of continuity. And so Professor Caffarelli mentioned this and talked about this earlier this week, and this is the type of theorem that we're looking for. So we'd like to get a similar statement in our problem, but as I mentioned, you don't have a uniform modulus of continuity for the obstacle. You only have a one-sided estimate. So you're going to proceed by controlling the oscillation of the solution kind of in three distinct cases, and that's going to help us just kind of propagate the estimate to u. So in particular, maybe you're going to look at a particular case where you can show a uniform estimate between 2 points where one is off the contact set and one is on the contact set. So these are the distinct cases to keep in mind. So from a top-down view, the first case is to just take a point here. So this is case 1, and you have a point here. The second case is to just consider 2 points on the contact set. So this is the set u equal to phi u, and this is the set u less than phi u. Okay. And the third case is when you actually want to take 2 points within the interior of the non-contact region, and that's going to two distinct cases where you have 2 points far away. So here, in this case, this is where you apply the interior regularity estimates for the operator. And in the other case is when you have 2 points close enough that they're close to the free boundary like that. So you can do kind of a projection. And you want to control the oscillation in this fashion. So this case is OK, right? This just follows from interior regularity. So the two main things we need to show are essentially that if I have a point off the contact set and a point on the contact set, I can have a uniform growth away. And the other thing that you really want to prove is that if you have 2 points on the contact set, you also have a uniform growth. So in some sense, having a uniform growth on the contact set tells you that phi of u c omega r on the contact set is bounded by a constant. So in fact, you can increase from a semi-concavity modulus to a full modulus of continuity for the obstacle on the contact set. And if you can do that, then you can prove all these distinct cases and then prove the estimate for the solution u. So, okay, so what was the idea? So the idea here is let's look at the Laplacian again, and let's just do a simple mean value theorem calculation. If you do a simple calculation for the mean value theorem using the mean value theorem, so here, take the Laplacian, subtract off the linear part, and fix a point off the contact set. And this lemma says that there exists a point on the contact set for which you can get the correct uniform modulus growth. So really the picture here that you should just have in mind, so I won't do the proof, but the picture in mind here is that essentially if I'm off here, I can project to a point here. Let's actually make this a little bit smaller. Let's call this a distance rho. And if I look at the ball, that's not good. Let's do this here. if I look at a ball of 2 rho around this point, and I look at this ball right in here of distance rho, so this is, according to my notation, this is x naught, this is x1, then you can apply the mean value theorem in the ball of 2 rho, and you can also apply the concavity estimate from the obstacle at this point, and you can use those two pieces of information to get an estimate on the solution u. So you do that, you do the distance, okay, subtract off the linear part, and if you apply the mean value theorem, you concentrate on this ball here, and then you look at everything outside of this ball. The mean value theorem for the point at x1 is going to evaluate exactly to the solution u of x1. And if I apply the semi-concavity estimate on the ball of 2 rho, then I end up with that line there. And from the mean value theorem, that just gives me the correct estimate from below at x1. So in the harmonic case, it's easy to see using the mean value theorem that you can find a point on the contact set for which you have the correct estimate. Now, this is that was really direct and very nice. And what we like to do and what we were able to do is, so this was kind of just recapping the 3 main points here for this argument. And then the main point here was to try and generalize this to the fully nonlinear version. And that's what we were able to do. The harmonic, so for this lemma, you should think that the harmonic estimate here is just kind of the Harnack inequality, right? And the estimate here, we kind of needed a weak Harnack or like an L epsilon lemma from the fully nonlinear theory. So using those 2 estimates together, and just for the context of the fully nonlinear case, I just set everything to CR squared to make the theorems look a little bit nicer, or the lemmas look a little bit nicer, but everything works for general modulus. You just scale with the appropriate modulus. And you can prove a similar estimate for the fully nonlinear version. So that kind of helps us with most of the cases. The last case that remains is the one where you have 2 points on the contact set. And so we need to improve the oscillation estimate here. And the idea really is that if somehow the oscillation estimate failed, like if I had a picture like this, so suppose this were the obstacle, this is the solution, and suppose the obstacle really did something like that, it went really negative, and suppose you had 2 contact points like that. Being really bad at one point by the semi-concavity estimate actually tells you that you can find like a whole half ball worth of points where the estimate fails. And so that just having a positive measure of points where things fail is going to be a direct contradiction to a weak inequality, like a weak Harnack inequality. So you can prove that directly. So that way you can actually prove that if you don't have the estimate, so this is the other lemma, so if you don't have the estimate for 2 points on the contact set, then you can just, it's actually just going, you don't even need the full Harnack inequality. It's just going to be it's going to be a contradiction to the weak Harnack inequality on the contact set. Okay, so with those 2 lemmas, you're able to prove for the fully nonlinear that solutions are C omega R, because then you can do, as I mentioned, the different cases. Okay, so what's our application? The stochastic impulse control theory. So in the previous section, as I mentioned, we obtained a general estimate for fully nonlinear obstacle problems with a general modulus of semi-concavity. So to apply this estimate, it's sufficient to prove that mu of x is semi-concave with the general modulus of semi-concavity omega r. So once you're able to show that, then you just apply the previous, and that'll give you the estimate you want for the fully nonlinear stochastic impulse control problem. As I mentioned earlier, that the strategy of the proof is going to follow ideas presented in Caffarelli-Friedman, and I'll try and present a little bit of that with the remaining time I have. And just one point to note is that you can actually prove existence and uniqueness of a continuous viscosity solution to the problem. And this follows a very similar iteration technique that's done in the Laplacian case, where you consider fully nonlinear obstacle problems that are not implicit constraint or don't depend on the solution, they'll converge by stability results for viscosity solutions to the solution to the implicit constraint problem. Okay, so here's the main lemma that we want to prove, that if I assume omega r is semi-concave, and the assumptions that I had, strict positivity, bounded and decreasing in the positive cone, then the obstacle is going to be semi-concave with modulus of semi-concavity omega r. Okay, so there are two distinct cases to consider to do this. The first is you first want to argue that in a neighborhood of a contact point you have semi-concavity, and then you want to consider a point that's not on the contact set, and you want to prove uniformly in a neighborhood around there that you also have the semi-concave estimate. So the way that this goes, and this follows very closely the ideas presented in Caffarelli and Friedman, is you're going to study this set here. So this is just the set of all vectors living here. And this is going to be the set where, so to characterize this set is actually the set of values, the set of psi values out here for which U achieves its minimum. Okay? And that's actually the context of the first observation. I mean, if it wasn't, then you would just get an inequality like a value out here would be strictly less than the infimum of U far away. And so that tells you that those values have to be the minimum values. So that's the first step. So there's kind of this set sigma naught floating around out here. So I'll call this sigma naught. Yellow might be better. Call this sigma naught, just a picture to have. And these are the set of minimum values that U takes. Okay. So the next observation to make is that for a point on sigma naught, you're actually, so I wrote it out here, but it's not on the contact region. Every point on sigma naught, actually, you get the following inequality, that U of x has to be strictly less than mu of x. Okay? So you can prove that directly. So this is something, so this is a lemma. And so in particular, with the continuity of U, you can prove that there's a neighborhood N1, depending on the point X at this point, where you have a C11 estimate, right, for the solution. This is from the obstacle. This is from the operator. So once you have that, then it's not hard to show that you can actually improve that by showing that this thing is actually strictly away for uniform delta naught, away from the contact set. And the argument is, if it weren't, you could take a sequence of points, and in some sense, that point is going to converge to a point on the contact set, and at the same time be on sigma naught. And so from the previous lemma, you'd get U equal to mu of x, but it also has to be strictly less than mu of x. So that would be your contradiction. And so in that sense, this set actually has to be strictly away from the contact set. And so this is actually an interesting lemma. The last lemma here, last observation to kind of make about this is you can prove a kind of continuity property for sigma naught, that if I look in a neighborhood around a contact point, then there actually exists a neighborhood around here for which, if any point in this neighborhood is on the contact set, then the infimum values for any x here have to be realized in some delta neighborhood over by sigma naught. So this is a continuity property of this set. So actually, not only do you have just one point, for one point does it live far away, actually for a whole neighborhood of points, you can actually get that the infimum of U is realized far away. So what's the point of this lemma? The important thing about this lemma is that it allows us to kind of redefine the obstacle. So instead of having to consider the obstacle, so if I look at the obstacle just in a neighborhood of one contact point, it allows me to say that the obstacle only takes values in some delta neighborhood around sigma naught. So it restricts the domain of the obstacle. So what do I mean by that? So if I look at the obstacle in this neighborhood, then in fact I can consider the obstacle where the x naught plus c values live in this N3 neighborhood, let's say around here. And in fact, you can make it even smaller. You can take a smaller delta neighborhood here, kind of controls how small the delta neighborhood there. And in fact, you can do it so small that it's inside of that N1 neighborhood we found in the first lemma. And by doing that, what that allows you to do is that allows you to say that a whole neighborhood worth of points is far away, and then you can apply regularity estimates for u, because if you live far away, then you satisfy the equation. And in fact, you can control second incremental quotients of u far away. And then by the semi-concavity of phi, we see that if you take second incremental quotients of mu, minus 10. Oh, geez. Sorry. Okay. If you take, okay, the last slide. Do you mind if I just? Okay, I'm very sorry. Apologize for that. If you take the second incremental quotients of mu, they're the same as the second incremental quotient of the phi plus the second incremental quotients out here. And in fact, you just prove that up to C1 when you have the same modulus of semi-concavity for the obstacle as you did for phi. Okay. All right, so that's good for the contact point. And the non-contact point is actually much easier once you have the contact point, because this just the observation that the infimum of u on the positive cone for a non-contact point must always be realized at a non-contact point, because if it's not, and from the previous lemma, you can find a set far away where it is realized, right? So it's always realized far away. And plus, you have a uniform or delta neighborhood around the contact set for which points they're always going to be realized far away. So in fact, you can do the exact same argument we just did. You can bound again the second incremental quotients. So thus, in a neighborhood of a non-contact point, you get exactly the modulus of semi-concavity for solution u. And with that, we just have some work in progress that we're doing. We're thinking about the thin obstacle problem. The free boundary estimates are completely open, something to work on. And just in general, it's kind of a pitch for quasi-variational inequalities. There are just so many models that pop up in mechanical engineering, electrical engineering, quantum engineering, robotics, image processing, economics, and math finance. And this is completely open. I mean, nobody has really worked too much on regularity estimates for solutions of quasi-variational inequalities. So with that, thank you very much for your attention.